Hello, everyone. This is Elisa Baum. I'm GridGain Systems Director of Product Marketing. We'll begin in just a moment, but first I need to conduct a little bit of housekeeping. Can you please raise your hand using the hand icon in the GoToWebinar control panel to let me know if you can hear me? So let me see. I see hands. You guys are very helpful. Thank you. Next, during this presentation, you will be on mute, but should you have any questions at all, please enter them in the questions window in the GoToWebinar control panel. At the end of the presentation, we'll take time to answer as many questions as possible. So with that said, I'd like to introduce today's speaker. It's Dmitriy Setrakyan. He is GridGain Systems Chief Product Officer and co-founder, and he'll be presenting memory-centric architecture in financial institutions. And with that said, I'll turn the floor over to you, Dmitry.
All right, thank you, Alyssa. So I'm Dmitriy Setrakyan. I'm one of the GridGain founders. I currently play a role of Chief Product Officer at GridGain, and I'm also a PMC member of Apache Ignite project. So, don't I have a difficulty? Oh yeah, now it works. So what let's take a brief look at agenda. What we're going to be talking today, as Lisa mentioned, the whole focus of this presentation is about memory in-memory architecture, so memory-centric architectures for financials. Why, what, and how. That, and then we'll go over Ignite overview and how Ignite compares to other storage systems available today. We'll take a look at a Sberbank use case. Sberbank is one of the largest financial institutions in Eastern Europe and Russia. They're one of the largest GridGain users and Apache Ignite users. I would say largest Apache Ignite users and GridGain customers. They are also deploying one of the largest distributed database / data grid architectures in the world, so their use case is very interesting. So we'll take a look at their use case, what's important to them, why they moved to this architecture, and then we will look at some of the challenges they've ran into, because when deploying a cluster this large in such a mission-critical environment, we've definitely run into some challenges, and we'll talk how we noticed them and what steps we've taken to resolve them. And then we'll move to Q&A. So as you proceed, you can feel free to type in questions, as Lisa mentioned. Type in questions in the window, and at the end of the presentation, we'll go over all the questions that you have asked. All right, so let's start. Let's actually start by looking at the use cases for financial services and overall financial market. So the in-memory computing overall is one of the probably most important kind of architecture deployed today in any financial institution. Matter of fact, financial institutions is the industry that pioneered in-memory computing, obviously because of the strong performance requirements that are needed for most of the use cases in financial. So we can take a look at some of them. I mean, if you've heard about T+3 method, essentially it's a method. It's a method which takes 3 days, the financial transaction. Essentially, that's how long it takes to ensure that buyer has the money, seller has the goods, and all the contractual and risk analysis that needs to be done to execute every financial transaction. So for a long time, this type of settlement took 3 days. Today, with in-memory computing, we can do it in real time. It's called straight-through processing. So now we don't even have to wait at all, and all the settlements happen immediately, most of the time. Other use cases include high-frequency trading, fraud detection, retail banking. If you will look at high-frequency trading, obviously, we have to make their decisions within nanoseconds. And the decisions are based on analyzing large amounts of historic data in order to make a decision whether to buy or sell a certain financial instrument. So goes without saying, you cannot achieve this type of latency with traditional disk-based architectures. You have to perform most of the computations in memory, and that's where that's exactly what high-frequency trading, algo trading is using. Fraud detection. For a long time, fraud detection meant if somebody reports something fraudulent, at that point a financial institution would take action. Now every institution is being smart about how to catch, how to detect fraudulent activity, and the longer you take to detect it, the more money will be stolen or fraud. Essentially, like if we can look at several examples, let's say using your credit card at a gas station in California, and within, let's say in San Francisco, and within 2 hours you're using the same credit card at a gas station in Los Angeles. Something like this obviously should trigger an alert, because you cannot be in two places that are so far apart within a span of 2 hours. And if you detect it in real time, you can actually reject the transaction. If you detect it in 3 days, then you actually accept the loss. So the sooner you detect it, the smaller the loss will be. And that, so obviously, use cases like fraud detection have to do analysis in real time, have to analyze behavior in real time, and have to make decisions in real time. And that's where most of the architectures are using in memory computing today. And of course, retail banking it used to be that we used to walk into a branch in order to perform a financial transaction, in order to add a deposit, do a withdrawal, or pay bills, etc. Now all of that is happening online. So we literally moved from thousands of iterations per day to millions of iterations per second. And of course, when you have such a leap load and in load and volume of operations, the traditional architecture for which was built, which the system was based on before, is not going to work anymore. And by the way, this use case is pretty close to the use case of Sberbank, and I'll be talking about a retail banking use case in more detail down the road. So let's actually look at some of the technical requirements now that we've covered the use case. So time is money, forgive the cliche. Millions of transactions per second. So it's millions of transactions per second. So the system has to be able to process huge amount of transactions with minimal amount of latency. So the system has to be able to scale to such type of load. Asset consistency. So that's another requirement that's specific to financials. Essentially, if you look at many scalable systems today, most common architecture that comes to mind is NoSQL architecture, which obviously does not have strong consistency built in. It has eventual consistency built in. However, a financial operation cannot be based on eventual consistency. When you're dealing with money, you need every single subunit of a transaction to either succeed or fail as a whole. You cannot have them to get inconsistent for a little bit and then eventually consistent. This simply does not work in finance when it comes to money. So asset consistency is a strong requirement. And of course, durability. Imagine what would happen if the system wasn't durable and your last deposit that you made into a bank was lost, right? So not a single byte of data should be ever lost. And it should utilize familiar APIs. Most of the systems, most of the architectures used in traditional financial institutions are SQL based. So the new architecture has to be able to talk to the data using SQL to the least. You can actually add additional APIs, but SQL minimally has to be supported. So let's take a look at the architectures that we're seeing today in financials. So traditionally, for a long time, and most of the financial institutions probably are using two-tier architecture, what I call SQL-centric architecture. Essentially, there is a centralized database, usually some sort of RDBMS, maybe Oracle, maybe MySQL. And then there is an application layer sitting on top of that database. The more load you have, so generally this architecture has one box. The database is deployed on one box. And the more load you have, the more throughput you have, the bigger the box you're going to get. So as your load grows, you constantly have to buy a bigger box. This is what we call a scale-up architecture. It's very expensive to scale this way. And it doesn't provide horizontal scalability. It doesn't allow you to add servers on demand. It doesn't have the elasticity component to it. To give you an example, most of the scale-up architectures will support failover. So essentially, they can have a backup database which will take over in case of primary database crashes or goes offline. It does not have an elasticity component. As an example, think about it. How many times have you seen a deployment of cluster of 20 or 30 Oracle database servers working together? Probably never. So usually it's one or two. All of them are deployed in a failover fashion, and all of them are fully replicating one to another. So that's the limitation of a scale-up architecture. It cannot support the growing data load. So what does a new architecture need to have? Essentially, obviously, it needs to be able to scale horizontally. As the load grows, we need to be able to add and remove servers on demand. And the more servers we have, it has to run on a commodity hardware. We do not need expensive hardware, or should not need expensive hardware to support financial use cases. It has to be, of course, always available and durable. It should never go offline, and it should never lose data. It has to be transactional, because we do not want to have inconsistency when it comes to money. We always want full consistency. And it has to be fast. Essentially, if the architecture is scalable, right, then you just moved from a data that was all located in one place to the distributed data. Now every server has a portion of the data, and the whole data set is split up across multiple servers. So now to compute on that data, to process transactions on that data, you want to make sure that in your architecture, in your design, you have as little data movement as possible. And when the data is distributed, the only way to achieve it is to send your logic to the data. Avoid sending data to the logic. So if you think about traditional client-server approaches, like, for example, JDBC works in this way, or any kind of database driver works in this way. You access a database remotely, you bring data to the client, you process it there, and discard it shortly after. The new paradigm actually should also support bringing your logic to the data. If you bring your logic to the data, then logic is very lightweight. It's usually just a compiled class, and usually just a very small message. And most of the data is exactly on the node, on the cluster node where the data resides. This type of processing is called collocated processing. And one of the systems that supports all these requirements today is Apache Ignite. We'll talk about it in a bit. So what is Apache Ignite? Essentially, it's a memory computing system. At the core of the system, we have a strongly consistent distributed database. Note that I'm not saying SQL database or distributed SQL database or no SQL database. I'm just saying distributed database, because the database actually supports multiple. Two main ways that most of the users will immediately start using are SQL and key value. You can talk to Apache Ignite using pure SQL APIs. You can create tables, you can create indexes, you can use NC99 SQL with it, you can delete and drop data from it, etc. It supports multiple ways to load data, ingest data, query data. So SQL is definitely first-class citizen within Apache Ignite. Another way to talk to the data in Apache Ignite is key value. And key value, should probably jump to the next slide. And key value allows you to actually access data directly by key, directly from code, by passing data and SQL drivers. So you're talking to Apache Ignite directly using key value API. And it also allows for collocated processing. It allows to send your computation to exactly to the server where the data resides based on a set of keys that you're planning to process. So once you tell Ignite which keys you're planning to process, Ignite will be able to immediately pick the servers that hold those keys and send your computations directly to those servers. This will enable local or collocated processing and will minimize the data move, which is very important in the distributed system. So this diagram actually generally shows high-level feature set of Apache Ignite. On the right, on the left we have Apache Ignite. On the right we have some enterprise features provided by GridGain. So some of those enterprise features include data snapshots, data backups and recovery, monitoring management, security and auditing. Essentially the functionality you need to deploy Apache Ignite in a mission-critical enterprise systems. Another thing to note here is the persistence aspect of. For a long time, Apache Ignite was an in-memory data grid, and which essentially meant that it didn't have its own persistence. The way Ignite supported persistence is by residing on top of a existing database. Could be Oracle, MySQL, could be Cassandra. We have many cases where Ignite sits on top of Cassandra, Mongo, etc. So essentially, it serves as a distributed data grid, distributed caching layer over a persistent database to provide some scalability and better scalability and performance for an existing system of record. With Ignite 2.1, which was released in June, Ignite now added its own native persistence component. And the reason it was added is because most of the users, many users, should not say most, but many users were commenting on the fact that they probably, or that they already know how, they're already using Ignite exclusively to talk to their data in their code. And there's no actual advantage for them to have yet another architectural piece, another database in the system. It would be cool if Ignite could persist data itself and could become a system of record. So based on that feedback, the community has added the native persistence, which is native to Ignite. It's part of Ignite open source. So if you download Ignite, you can actually immediately start persisting data to the disk. And it's a distributed persistence storage. So essentially, it's a fully durable, it's a fully transactional. It's, as I mentioned, it supports SQL and key-value APIs. And if you enable it, you essentially do not have to use any other third-party persistence mechanisms. Note, however, that Ignite also supports using both persistence mechanisms in conjunction. So you may actually start using Ignite in memory if you do not want to disturb your existing database. You can start utilizing Ignite in memory. You can deploy it as a caching layer, as an in-memory, distributed in-memory layer over an existing database. As you migrate the system into using Ignite APIs, you may at that point just switch a configuration switch and turn on Ignite persistence. At that point, you will actually start persisting to disk, and the system will become fully durable just based on Apache Ignite persistence. At that point, you may or may not wish to turn off a third-party persistence. So Ignite will work in conjunction or on its own, and will persist data on its own without any third-party persistence systems enabled. All right. Of Apache Ignite. So essentially, the takeaway point from this slide probably is that it's a distributed architecture. Every server has a main component called durable memory deployed. And what it means is that, what durable memory means is that it can work as memory only. So if it's a memory, if the persistence is turned off, then Ignite serves as an in-memory, like a full-blown key-value data grid in memory. Or you can actually, if you're using SQL, you can think of it as a distributed SQL database. Essentially, a distributed database that is purely in memory. Once you turn on the persistence, now you can actually store data sets that are larger than, for example, if your cluster can only fit 3, 4, 5 terabytes in memory, your disk can probably store a lot more data. So you can actually keep 4 or 5 terabytes in memory and maybe petabytes of data on disk. And that is a perfectly valid use case for Apache Ignite. And as a matter of fact, that's one of the use cases that I'm going to talk to in the context, or I'm going to talk about in the context of Sberbank. So let's first look how Ignite compares. So let's look at the storage systems today, the storage ecosystem today, and see where Ignite fits. So we'll start from a traditional RDBMS storages. Essentially, probably the oldest architecture that has to do with the data, with storing data, is an RDBMS architecture. Generally speaking, it provides one of the strongest SQL APIs. It's fully consistent, transactional implementation. Most of the RDBMS systems today do provide in-memory option, but these type of systems are not distributed, are not scalable. As I mentioned, they only support failover. They do not support elasticity. They do not support horizontal scalability. So that was okay for a little bit, for a long time actually. And then as the data loads grew, as the amount of data grew and the concept of big data came around, we actually started thinking on how to scale this architecture horizontally, because scaling up became very expensive. Time did not satisfy the data volume needs of lots of financial use cases. So as you start scaling out horizontally, people say, the common belief was that now that we're going to add scalability, we're going to have to remove transactions, because transactions at that time were very slow, were based on a single transaction server most of the time, and generally it was a centralized architecture with a lot of times single point of failure, etc. So transactions at that time were evil, and people decided to avoid them, and that's where NoSQL architecture came out, with a famous write-up from Amazon CTO, describing how their Dynamo database works and how they provide scalability. And essentially, these type of architectures usually mean very good horizontal scalability, very good availability, because a crash of a single server should not bring the system down. They are all durable, but they do not provide consistency. They provide eventual consistency. So the data can get inconsistent over time. So for a long time, NoSQL meant adding horizontal scale and removing strong consistency. So a distributed architecture was associated with no strong consistency. And then again, use cases came up that actually did require both horizontal scale and strong consistency, and that's where architectures like in-memory data grids and in-memory databases came about. And essentially, at that level, they said, because we're in memory, faster, transactions don't have to be slow anymore, but we'll still provide horizontal scale, we'll provide performance. Most of those systems do not support SQL. Some do, some don't, but pretty much all of them do not have a good persistence component. Most of them are not durable and rely on some other third-party database to provide durability. Like, as I mentioned, Ignite for a long time was an in-memory data grid, and was deployed as an distributed memory layer on top of an existing SQL database, or NoSQL database like Cassandra, Mongo, etc. So with MDG and IMDB, in-memory data grids and in-memory database architectures, now we said, okay, we can be fully consistent, we can be fully available, fully scalable horizontally, but we're going to sacrifice durability. Essentially, the system on its own, without the help of some other database, cannot be durable. So if you look at all these type of categories of data storage systems, you see that whichever one you pick, you have to sacrifice something. If you want horizontal scale, and you cannot have strong SQL support, you cannot have strong transactional support, Or if you have that, then you cannot have persistence, you cannot have durability, etc. So whichever way you go, you have to sacrifice something. And that's exactly the premise of why we added all this functionality to Apache Ignite. We wanted to ensure that our users don't need to sacrifice, or make huge sacrifices when they pick Apache Ignite. Apache Ignite is a fully scalable, horizontally scalable system. It can be deployed on a commodity hardware, any type of hardware that can run Java will work. It's fully available, fully consistent, provides strong consistency, as strong as it gets. Good enough for financial and money, good enough for moving money. Apache Ignite users move money on top of Apache Ignite distributed cluster. It has persistence, scale, key value APIs, etc. So the whole premise of Ignite is to make sure that you have everything that is important to satisfy today's financial. So let's take a look at the Sberbank use case. So essentially, Sberbank was hit with a common problem in retail banking, and most of the retail banks are being hit with the same problem today, and will start or have already started moving into a distributed architecture. So Sberbank actually again was hit with going online. So all of the operations moved from in-person operation to online operation. So every time you log in from your mobile device, from your computer, from ATM, etc., all those transactions happen in real time. So, and the system has to support millions and millions of transactions per second. So the architecture to support that transaction load had to become more scalable, had to become horizontally scalable, had to be based on open source technology, and without making any type of sacrifices that are important. So use cases like asset compliance, transactionality, SQL compliance, key value collocation, collocated processing, etc. So Sberbank is deploying one of the Sberbank picked Apache Ignite as the core of their architecture. And is migrating their core banking onto Apache Ignite as we speak. So have migrated some of the components that are already running in production, serving real-time use cases, and will continue migrating throughout the year of 2018. Sberbank will be deploying one of the largest data grids and distributed databases, distributed database clusters in the world. The cluster actually will have about 2,000 servers distributed across 3 data centers. The system will be storing 1.5 petabytes of data. So there's a lot of data to be processed, and all of that data has to be processed in real time. There should be absolutely no downtime for the system. The downtime should be measured in seconds. So that's why there's a lot of redundancy. There's about 4 copies of every key residing in memory. Apache Ignite actually capability of storing redundant key value pairs in memory and on disk for that matter, if persistence is enabled. And one of the important features that Sberbank wanted was immediate restart. So if you think about it, Sberbank actually has very powerful servers. They can load probably between 500 and 700 gigabytes of data in memory per server. However, if you think about it, if you think about the cluster is about 1,000 nodes or 2,000 nodes, and if you don't persist, then you have to reload the data in memory before you become operational. And loading this much of data in memory will take time. We're definitely not talking seconds, we're talking hours. And this type of downtime is not acceptable. That's why Sberbank needs to become operational immediately. And for that, we need to become operational from disk. That's where Ignite persistence comes into play, because it actually allows Sberbank to become operational immediately. And as they begin to access data, the caches, the in-memory caches will lazily load, and the consequence will become faster. All right. So just so we understand the scale at which Sberbank is going to be deployed, I'm going to bring up the world's biggest supercomputer, which is probably one of the largest clustered supercomputers known today. It's called Cheyenne. It has about 4,000 nodes. It has about 300 terabytes of RAM. Sberbank has over terabyte of RAM. So as far as in memory goes, Sberbank actually is bigger than Cheyenne. And it has about 50 petabytes of disk. Their Sberbank is smaller. But if you look at overall scale, it's comparable. So that's the type of scale, that's the type of deployment that Sberbank is dealing with, and we're helping them, of course. And of course, when deploying a use case, a cluster of this size, you're going to run into issues. First of all, keep in mind, this is probably the first in the world. This type of use case, this type of size of deployment for a distributed in-memory architecture is probably one of a kind. It's first in the world, and we expect a lot of problems that we ran into, nobody ran into before, so we had to overcome on our own. So, and let's take a look at some of the challenges we ran into. So challenge number one, large memory size. So Sberbank has about 1 terabyte per server, maybe between half a terabyte and terabyte per server. So any Java user, any Java developer will immediately say that deploying a Java heap of 1 terabyte is not an option. So you have heap size this big because you will start running very large garbage collection puzzles. And so if on heap is not an option, we have to have off heap. So off heap has to be the primary storage at Sberbank. And Ignite supported off heap very well all the time. And starting with Ignite 2.0, off heap is actually the primary storage of Apache Ignite. Apache Ignite will store all the data and all the indexes in off heap memory, which means that Java does not know about this data. Ignite manages this data outside of Java heap. Also in memory, it's still in memory. Enter access away, it's still very fast. However, we manage it on ourselves. Java does not manage it, so you're able to allocate much smaller heap size for your Java application and allocate large amounts of memory off heap because they do not affect garbage collection and do not create extra pods. So that was the first challenge. Instantaneous restart, as I mentioned, was the second challenge. Most of the in-memory systems will have some persistence component. But generally speaking, that persistence component is just a copy of what can sit in memory. For an in-memory system to become operational, the data has to be loaded from persistent storage like disk into memory. So it's okay, like it can be done pretty quickly when we're talking about a few terabytes. When we're talking about petabytes, it may take hours, maybe days to preload the system. So obviously you cannot satisfy 5-minute SLA with that type of design or that type of limitation in the system. And that's exactly why the system has to be able to operate directly from disk and warm up memory as it progresses, as it goes. And that's exactly how Ignite works. And the functionality we call instantaneous restart. So you're able to store more data on disk than in memory. And you're also able to become operational immediately. As the system starts up, it will read data from disk. It will perform SQL queries based on indexes that are stored on disk. And as those queries and index operations are performed or key value access is performed, the data gets loaded in memory and the caches warm up. And after that, the operations will become faster and faster because more and more data will be served out of memory instead of disk. All right, challenge number 3, huge data model. So traditional data grids or traditional database architectures, in-memory database or in-memory data grid architectures, generally will have about maybe 10, 20, 30, 40 caches in memory. So that's exactly what Ignite was designed for, and that's exactly what use cases Ignite was generally used in. However, at Sberbank, we were very surprised that now they actually have a very complex schema very complex database schema, probably more than of data, and that would require to create thousands of caches in memory and thousands of data sets on disk. So huge data model actually would require, and since Ignite actually has to keep track of how it maps data within the cluster, and the mapping itself is not dependent, or is not actually dependent on the amount of data. So you can have lots of data and have one mapping. However, each cache had a separate mapping in Apache Ignite. When you have 20, 30 caches, it actually didn't present a problem. When you have thousands of caches, you actually start running out of memory because this mapping starts taking place and more and more memory, and eventually it's actually the place you don't even productively use. It's just the place for the system to operate. So it definitely created a problem that we had to overcome, and we did that by grouping caches with identical configuration, because most of the caches will have identical configuration. So we group them together and have identical mapping and identical rebalancing policies for those caches. So in one physical cache, and all these data types would be split logically within that physical cache. So whenever a rebalancing happens, the physical cache gets rebalanced. So if you add more servers, the data will be rebalanced from a physical cache. So that part of the system wasn't affected. However, the mapping, now we have to have, instead of 1,000 mappings, we maybe may have ended up probably with 5 or 10 different mappings. We call them groups, mappings for groups. So essentially, that's how we solved this huge data model problem, by grouping identical caches together into logical caches within one physical cache groups. All right, backups and snapshots. Obviously, every database requires a backup capability. In case of Sberbank, as I mentioned, the use case is that the cluster is very large and it can never be down and it cannot lose data. So it's not that you have to be able to back data up. You have to be doing it continuously. Ignite actually, GridGain actually provides on top of this functionality is provided by GridGain on top of Ignite. Actually, allows you to take full backups. So imagine if you have to, Sberbank has over a terabyte of data. If you have to take full backups all the time, it will require a lot of space and it will require a lot of time for a backup to complete. So GridGain supports full backups and incremental backups. The incremental backups would actually only back up the delta between right now and the previous incremental or full backup. On top of that, you have to be able to restore not only at the point of when backup was taken, but maybe at the point of backup plus n, right? You want to restore at the point of time on backup plus 5 minutes or backup plus 10 minutes. So essentially, you need to be able to unwind write-ahead logs that were present in the system on top of any type of snapshot, and we call it point-in-time recovery. So, and that type of functionality needed to be supported. Also, think about distributed cluster. So a distributed cluster, you have maybe thousands of nodes, right? A backup, the fastest way to take it within the same cluster. So by default, the backup will actually be collectively between all the servers. You have your full backup, but you should also be able to copy that backup into some other storage and unroll it on a cluster of different size with different configuration. For example, if something fraudulent happened, or if simply like some bug caused some wrong behavior in the system, and you want to investigate what happened, you do not want to investigate on the system. You want to have a copy sitting somewhere else, and you want to investigate on that copy. However, nobody is going to have another 1,000-node cluster sitting redundantly somewhere else. So this copy has to be able to be deployed on a much smaller cluster. Maybe instead of 1,000 nodes, you may be having 20, 30 nodes. And obviously, the disk will be much bigger in that cluster, and the operations would be slower because from disk, but still possible to investigate and provide recovery strategies or data restoration strategies, etc. And last feature that I'll mention is transactional data center replication. So most of the distributed system will provide asynchronous data center replication, and a lot of times that replication will be non-transactional. So it will replicate data across atomically, so every piece of copy will be replicated. But maybe data will be replicated across in a different order, or in a different, or end up in a different with different transactional semantics. So that obviously does not work when it comes to financial data, when it comes to money. And for that, we are implementing a transactional DR. It actually is very likely to be based on snapshot and backup. So we'll be replicating data the first time, which is a full backup, and then incrementally with incremental snapshots and backups, we'll be copying those increments across also. So to be a lag, right? You don't want to do it in real time because without any lag, because performance will be sacrificed, right? But you do, so the lag, some sort of a lag, maybe half a minute to a minute is acceptable, but the transactional semantics are preserved. So every financial transaction, for example, in financial transfer, if you think about it, is composed of withdrawal and a deposit. So the result of a data center replication will be both of those operations. You will not end up with a state which only has a deposit or a withdrawal. You will also have either both or not. So those are the kind of transactional semantics that are required for this type of replication. And that's what we're currently working with Sberbank on, and we'll provide it likely by the end of Q1 next year. So with that, I will actually stop and move to questions, if there are any.
Hi, Dmitry. Can you hear me okay?
Yes.
Okay, so the first question is a comment and a question. So 1 terabyte per node, and you said 2,000 nodes, which means 2 petabytes of data in memory. Very impressive. How is the whole data set? I'm assuming how large is the whole data set?
So, so the question is, if you have over a petabyte in memory, what is the whole data set size? So in case of Sberbank, it is exactly the whole data set size. They don't have a problem of loading the whole data set in memory. They have a lot of memory. The reason they require persistence is for resiliency. If the data center crashes and needs to be restarted, it needs to become operational right away. And to load all that data in memory will take time. So the system needs to be operational from disk, as I mentioned. So the whole data set is exactly between 1.5 and 2 terabytes, but it's also identical in memory and on disk.
Okay, next question. What about security?
So from a security standpoint, I mean, again, GridGain provides a security component on top of Apache Ignite, and it allows to integrate with service that you may have, be that LDAP, Active Directory, etc. And from that standpoint, every node and every client joining the cluster has to be authenticated, and then you can authorize every operation. So, for example, a certain connection may be allowed to do only read. Another could be doing read and write. Another could be doing administration. Another could so every type of there are multiple roles, and every type of connection to the cluster will be assigned or prohibited from and certain data. And those are configured on per cache basis. And you can have certain caches that are accessible by everybody. When I say cache, I mean a memory component, and if persistence is enabled, also persistent component. So certain caches can be allowed to be accessed by everybody, others can be very restrictive, etc. So that's how security is controlled within the cluster.
Okay, the next question. How does this strategy compare with spanner stretch clusters?
Point actually. So Spanner, I would believe that the reference is to Google Spanner, which is a distributed SQL database on the cloud. So there are some similarities between Apache Ignite and Google Spanner because both are distributed systems, both support SQL access, both support strong consistency and transactions. So from that standpoint, they're similar. The differences comes, first of all, one of the most obvious differences is that Google Spanner can only be deployed on Google Cloud. Ignite can be deployed anywhere, including Google Cloud, Amazon Cloud, or in any kind of private cloud environment, private data center. So that would be number one. Another difference would be key value API. So Google Spanner is an SQL database. The only API it supports that to talk to the data is SQL. So Ignite, as I mentioned, has several ways to talk to the data. SQL is just one of the ways. It also supports key value and collocated processing. So from a scalability standpoint, you could actually sell computation to an Ignite node, right? If you have 100 nodes in the cluster and you need to compute on a certain key, you send your computation exactly to the server where the data resides. So you avoid data movements within Apache Ignite. However, on a spanner, you would have to access it using traditional SQL drivers and bring the data to the client. So there is a lot of data movement in that sense. So I would say Ignite is more flexible and provides more scalability options than Spanner. Not to take away from Spanner because it's actually pretty cool that SQL deployments, I think, in the world. However, it's geared exclusively towards cloud use cases. And Ignite is built towards supporting both cloud and on-premise private data center use case.
Okay, next question. Is the system able to cope with the million per second during cache warmup? And what reasons justified restarting the full cluster in the case of this bank?
So there are two questions there. So first of all, during warmup, is the system still able to perform units of operations per second load? I would not be able to tell an answer to that exact question, but I would say that if you constantly have to read from disk, the performance will suffer. So obviously, initial reads from disk will be slower during the warmup and will become much faster as the memory warms up and most of the reads happen from memory. So in that sense, there is going to be performance degradation during the warmup, certainly. However, it's still better than having no access to the system whatsoever. So it's okay if a certain operation takes longer. We're talking about latency. It's okay if latency increased. However, the throughput did not decrease, right? You are still able to process the same amount of users. You're still able to process the same load. And the reason for restart of a cluster could be anything. Could be a power loss. So any kind of force major disaster that may happen in a data center that will require over to another data center. At some point, you want to switch back to the original data center. And in that case, you probably, if it was a power loss, you have to restart it and you have to do it pretty quickly. So that probably the type of cases when you have to restart the cluster. There are probably a lot more than that, but they don't happen often, but when they do happen, you have to be able to support them.
Okay, next question. What level of access application has to write ahead log persistent data?
Can you read the question again?
I believe it's what level of access does the application have to write ahead log persistent data? Does that make sense?
I'm not sure I understood the question. Not really. I'm trying to understand the question. There's definitely a write-ahead log, and there's definitely a main storage. And whenever data is updated or inserted into the system, first and foremost, it ends up in a write-ahead log, assuming the it ends up on a write-ahead log. And then there is a process that will checkpoint this data from. So when the data is written into write-ahead log, it's also marked as dirty in memory. So the pages that's been written to write-ahead log marked as dirty in memory. And there is a process called checkpointing process that will go through memory, take all the dirty pages, and persist them to the main storage. At that point, those from the write-ahead log. So I'll stop there because I can explain how the architecture works, but I didn't really understand the question. So if you still have a question, please ask it again and I'll try to answer.
Okay, thank you. Let's see. So the next question is, what's the improvement still envisioned for the system you described? Things you would like to work still better?
So what can we do better? I would say, well, I mean, first and foremost, performance. I think the focus for the next year would be to constantly performance and usability. I think the community just implemented a very big piece for persistence, completely changed the architecture, going to off-heap architecture. So we're meeting some questions on the user list that have to do with the usability of the system, which we're focusing on. Some has to do with performance in certain use cases, which we also immediately focus on. Another focus would be SQL. I think supporting more and more SQL use cases in easier fashion and in more performant fashion is probably the focus for the next year. As far as adding major functional pieces, I think the community on one major piece, which is currently in beta, is machine learning. So if you already have data stored in Apache Ignite, you are able to apply machine learning math, machine learning algebra, top of that data to add intelligence to it. So the whole reason here is to make sure that you don't have to copy yet again this data to some other system to perform machine learning. You can actually perform your machine learning use cases directly on top of Apache Ignite. So that would be like some short-term roadmap in the nutshell.
Great. Okay, so another question is, if I have less memory than what is in the disk for a node, then during restart, which data will be preloaded? How do you control it?
So there are two questions here. So first of all, I'll say that in Ignite, you can configure different caches or different data sets, if you will, as in memory only, or in memory and disk as a copy of each other, or disk as a superset of the data that resides in memory. So you can have three types of data sets, and you get to pick and choose for each data set what kind of configuration you want. You can, some data that you need to have available very quickly at all times, you actually store in memory only. Other that is maybe has to be durable, or has to be less performant, or has to just is big, so big that cannot fit in memory. You can actually store on disk. So from that standpoint, you can actually have three types of way you work and store your data. Is not required. You can have preload if you want to, but preloading is not required. You can the system becomes operational directly from disk. Memory warms up as it goes, and as it warms up, the operations will, the caches warm up, and the overall performance of the system will increase. So there is no preloading requirement, unless you explicitly tell Ignite to preload certain data set in advance.
Okay, we have time for a couple more questions. So are they using Kafka, Spark, Elasticsearch, or is Apache Ignite taking care of all these things?
No. So Apache Ignite is a distributed database. It's not an Elasticsearch. It's not meant to compete or satisfy messaging use cases like Kafka, or text search use cases like Elasticsearch. It's more of a distributed data storage that is fully transactional, strongly consistent, and that actually is meant to support large amounts of transactions in real time or large amounts of analytical requests in real time. Elastic, if you have text search use cases predominantly, I would recommend that you stick to Elasticsearch. As far as Kafka goes, most of the Apache Ignite deployments today happen in conjunction with Kafka. So even Sberbank use case that I've been talking about uses Kafka to ingest the data in the system. So as the data comes in, it gets put on a Kafka queue and then taken from there and inserted, updated, or within Apache Ignite distributed cluster. So Kafka is something that Ignite integrates with very well. If you look at Ignite community, there are several ways to integrate with Kafka, several components that come out of the box directly from Ignite.
Okay, great. Well, this brings us to about the top of the hour. So I wanted to thank the audience for their participation today and all the great questions. And Dmitry, fabulous job as always. We hope that you join us on a future webinar. If you go to www.gridgain.com, we have several posted and I'll be adding even more. So we hope you join us in a future show. With that said, Dmitry, thank you again so much for the presentation today.
Right. Thanks everyone for listening.
And also, I will be sending a link to this recording as well as the slides after the event is processed. So again, thank you, everybody.